Good. We'll record.
All right. Happy Wednesday. Glad you could make it for the talk on deep learning. We're going to have in 3 Saturdays, I think.
2/3.
Kind of a counterpart or a follow-up of sort of a hands-on, or we're going to go through an example. It may be sort of like a cooking show of here's some stuff, and then, hey, look, there it is, the turkey's done. So we'll have a model cooked probably, and maybe some small interactive, smaller things that you can do for yourselves. Laptop, you may have to put something out there, kind of download this stuff or get these things to be prepared for it. But that's what's coming next as a follow-up to this, kind of the hands-on part. So that'll be fun. I'm Alex. I've been hosting this meetup for a while, and it's good to see the group that is coming out now. We're getting to some more hands-on coding, people that have an interest in the coding side versus more theoretical and entertaining side of listening to these talks. So that's good. What I like to do usually is go around the room and let everybody introduce themselves, kind of who you are, why you're here, or what you are looking to learn, or what you know, or just kind of so people in the room know. You guys already do, but I may not. So, and maybe specific interests so that we can know maybe what, after this next one, what's the next talk that we have, and then we'll have like a demo day kind of thing after that, like what are topics of interest. So this is the one we're starting with. So I'm Alex, I work for AOL, who's owned by Verizon, and I work on their data platform. So I'm moving data around with Kafka, streaming big data around. Might be getting lucky to switch over to work for a company within our company, which is Convertro, who does multi-touch attribution models, deep neural network learning kind of things on, someone saw an ad on their phone, then they saw it on their desktop, then they saw it on their tablet, and they bought something. So kind of chaining together all of the things that happen, all the people online, you can kind of keep track of that. So that's one of their machine learning companies that I might get to switch over and work on their team. So that'd be really cool if I could do that. That would be fun. I'm moving data now, then I get to process it. So that's cool. So that's me. There cooler and chips and drinks back there. So grab one if you want. Let's go around the room and we'll introduce.
My name's Alex. I'm just tagging along.
All
Pretty
right.
much my wife. Active duty military. We're stationed here. We're from California, and go to school full time. No, part time. Sorry. Go to MGCC right now.
I'm Jaya. I'm a student, full-time student, and I just want to learn more about other programs besides what I'm in finance school.
Anything that you would look forward to and talk next time, keep that in mind. So, are you doing computer science as well?
No.
Yeah, but I think I'm more interested in web development.
Okay.
That's what is interesting to me.
Okay.
That's what really caught my eye in this semester.
All right, that was interesting and engaging, so you wanted to do more?
Yes.
Cool. All right.
I'm Ham, and I am also a student at USM, and just really interested in learning more about deep learning and data. So, yeah.
Anything, next talks? Get your
Um,
vote in now.
data.
More data.
Hi, I'm Lena. I'm also a student at USM, and I'm a computer science major. What I want to, for future talks and things, I actually want to start working on projects with them.
Yeah, cool.
Okay.
I'm looking forward to it.
Okay. Very good.
I'm Rick with that. work at the Bow, but I'm also a freelance web developer. That's what I do, you know, trying to get my foot in there, out there in the world with that, try to get in where I fit in, type of thing, you know, this whole developer thing.
Okay. Any particular next talk? You seem kind of fond of learning about PHP.
Yeah, well, I took a class from PERT on PHP and MySQL. Well, MySQL was part of the thing, you know, but I'm wanting to get a little more into the, you know, not just the front end, but the back end too. The whole stack thing.
Web stack kind of deal.
Yeah.
All right.
James Foster, I'm a programmer, system administrator, database at Coastal Family Health. What I'm really interested in is actually how to set up the environment. You know, what tools, what pre-installs, what base OS. Working on a project would be great because, you know, I've done some fuzzy logic. I've done a lot of fuzzy logic, but not neural net and deep learning, more just the mathematical modeling.
Okay.
So, but what I really am interested in is like, how do I go from 0 to, you know, half?
Anything to
Just get started.
Yeah.
So yeah,
You're Amy's friend, right? Amy Travis.
I'm sorry, what?
You're Amy Travis's friend, right?
No,
You have the, okay, all right. Sorry, I thought you were somebody else.
no problem.
I'm Brian Cooley. I'm have a company. I do freelance mobile development and machine learning or development work. And just addicted to learning. I like to learn new things and talk about them, even when I don't really know what I'm talking about. And I would love to do a project. That would be a lot of fun. I'm totally into that kind of stuff.
it's come up a couple of times, so you know, maybe we'll do this next thing. Will be a hands-on with this data thing, and if it's a project and it's data and it's setting up data, then we've got a lot of people who could do something more significant, perhaps.
I think better just to move on because, like, I was thinking we can talk about the end, but like, there's a lot of like building blocks to be able to do this stuff. Like, you got to install Python, you got to install all the libraries, you got to know how to program Python, trying to know how to work with it. So maybe 3 hours maybe hard to. We'll talk about it.
Good. All right. Well, let's get to talking and hearing about the presentation for Brian.
All right, I'm gonna sit here unless everybody can hear me okay. Doesn't have any desire to see you standing in front. I'll just stay out of the way. Yeah, so last week we talked about deep learning and just, you know, trying to learn some more about it. So I thought today we would just kind of, this is not a super technical talk. Like, it's not gonna, I'll show a little bit of code at the end, but kind of just want to get everybody with the nomenclature and sort of like a baseline to go from that we can build on in the future. And so, anyway, just to start, I thought we'd start with a little audience participation, talk about, you know, what learning is, and then deep learning is really just about neural networks these days. I mean, there's more to it, but it's really the driver behind all of the deep learning technology now. So we're going to talk about neural networks and just kind of like make a quick trip through the background of where they came from and why all of a sudden deep learning is you know, the big deal that it is. And then we'll talk about exactly what a deep neural net or deep network is. Not that exciting, but and then some things you can do that sort of qualify as deep networks and how they're used. And then at the end, I'm going to do a very brief demo on one of the sort of unfortunate things about deep learning is that it can take anywhere from like 30 minutes to 2 weeks to train a deep learning model on a data set. And so I didn't figure you guys wanted to stay here for 2 weeks while we did that. So anyway, what I'm going to do is I'll just. I know. But I'll just show how to use a deep learning model that's already been trained to make predictions, and we'll just pull some stuff off the internet and show how we can do that. Okay, so what is learning? What are your ideas? What is learning? What constitutes learning, and specifically in the context of how a human learns versus how a machine might learn? Any ideas about that?
Not committing the same mistake.
Okay, that's very good. I like that. So reducing incorrect responses. I like that. Anybody else?
Feedback.
Feedback.
Learn through trial and error.
Okay.
And so there's the feedback loop.
All right. So try something and get some information and make an adjustment on that. All right. Like that. That's a good one too. Anybody else?
Let's say like making relations between things and like maybe starting off from a template instead of each one.
Okay. Very good. I like all those are very good definitions. And usually, like you go to some sort of textbook about what learning is, you'll see something like it's a permanent change. You do something and you increase your knowledge. It comes from experience. So you've got data about the world around you. You want to try to internalize the data so that you can use it later. And like Nina said, you want to, if a response is correct, you want to strengthen that, and if it's incorrect, you want to try to weaken it. And so those are all. A lot of times we try to like differentiate what a human learns, how a human learns from maybe a machine, and we say, well, that's not really learning, but all of these things are fairly descriptive of what machine learning is, which is usually the problem of taking a set of data and building, like Pam said, building a relation that you can use later for prediction and classification. I would say probably the one thing that, and there are different classes of artificial intelligence. There's one called ANI, which is artificial narrow intelligence. And then there's AGI, which is general intelligence. And then there's ASI, which is super intelligence. The difference is like a narrow ANI, narrow artificial intelligence, would be more or less like I tell you what you're going to learn. I give you the model structure, and you fit the data to it. And that's really kind of where the state of the art of artificial intelligence is. Like computers don't really decide what they're going to learn in artificial intelligence structures right now. They don't say, oh, hey, I need to go train myself how to identify, cats from dogs and pictures on the internet, or wherever. You set that problem up for the computer and give it the data that it needs to fit a model that can do that prediction. So like I said, deep learning is basically about neural networks. And so kind of neural networks are an idea that have been around a really long time. People were studying the brain, the early part of the 20th century in the early 1900s. And in the 40s, as mathematicians were developing models of computation, it was sort of natural that they would say, like, hey, we should build computers like a brain works. And there were actually computer architectures that were designed to sort of mimic the neural network structure of the human brain. And the first neural network that was used in the real world was actually built in 1959 in hardware. And it was for reducing echo in phone lines. And it's still used today. So,
SS7.
what's that?
SS7.
I know it's the Stanford name, which is Madelman, or Adelman. Madelman is the multivariable version of Adelman, which is, I don't know what the acronym stands for. And so neural networks, as I'm going to show you in a minute, are they're basically, they can have multiple layers between the input data that you give and the output data you use to fit or that it will predict. The first multi-layered network came about in the 70s, 75 actually, and that was kind of that was the point where neural networks were at the stage where they could be as useful as they are today. Problem was that, you know, computationally speaking, we just didn't have enough power, and data-wise, it was almost impossible to get enough data to fit a complex network. The 80s were very, very popular time for neural networks. There was a company called Symbolics that built what are called Lisp machines, symbolic Lisp machines. Lisp was the programming language that was used to program AI. But then in the late 80s, there was all this promise about what neural networks were going to do, and it didn't happen. Symbolics failed as a company, and they call that the AI winter. So from like 89 to maybe 95 or so, there just was no investment, and it also happened in the late 70s, but it happened again in the 90s, and then it's kind of gotten popular again. In 96, there was a computer that played chess called Deep Blue that beat the then world champion Garry Kasparov. Although that was really not deep learning, and that was more of like a knowledge-based artificial intelligence system. But it kind of got the whole idea of artificial intelligence going again. And there was a lot of development between 96 and 2006. 2006 was when a researcher from the University of Toronto named Geoffrey Hinton coined the term deep learning. And what it specifically referred to was neural networks that had multiple layers. And what a lot of people were doing at the time was they would do this thing called feature engineering. So like, if I wanted to say identify a face, I would teach the computer. I would like figure out what does an eyeball look like in an image, and I would sort of teach the computer that. Well, in deep learning, you don't actually teach that. You just build this network and let the computer figure out if it needs to know what an eyeball is or what an edge is, or any of that sort of stuff. In 2012, there's a thing called the Large Scale Visualization or Visual Recognition Challenge. It was put on it was a contest that Stanford sponsored. It consisted of 150,000 images that you would train your whatever model you build, train your model on these 150,000 images and try to classify them into 1,000 different categories. And that was when this convolutional neural network called AlexNet, which was named after one of Geoffrey Hinton's PhD students who did the research, it won. And it's been, and that since that sort of sparked a lot of the research in computer vision using deep neural networks, convolutional networks. And then the latest, really like the latest accomplishment has been that I think it was DeepMind that Google built what they call AlphaGo, which is a dual neural network system that is actually able to beat humans at the game of Go. I don't know much about Go. I know it's like orders of magnitude or harder than, or orders of magnitude more branches than chess. So like in a game, that's the branching factor is the big deal, because what a traditional artificial intelligence knowledge-based system would do is it would just like search everywhere. Do like an exhaustive search, and then you do all these tricks, like you prune and other things to the search tree to make it more efficient. But Go has like a branching factor of 400 or something.
Chess has a finite number of moves, even though it's super large. It's still finite, whereas Go is infinite.
Right. So, yeah, and apparently in the competition, the the AI was coming up with moves that, you know, grandmasters and Go, you know, moves and strategies that they had no understanding of. So it's kind of sparked a new research into actually how to play that game the most effectively. And so really the driver behind this like explosion in the last 10 years or so has been the incredible accessibility of data between, I mean, there was Flickr and, you know, Facebook and Google Photos, and there's all these photos available, and storage is, you know, better, and transfer rates are higher, and it's just ubiquitous to have all of this kind of data that you need. I mean, even like you think about speech, and all the people that are using Siri or Alexa or all of these other devices that capture your speech, it's just creating huge amounts of data. And then the other thing that happened was really it's kind of a I don't know if it's ironic necessarily, but it's an interesting thing that the rise of like console games, Xbox and PlayStation and all of these things are very compute intensive for the graphics, if you want to do like realistic 3D graphics. And so they developed these graphics processing units that are really good and really fast at doing matrix calculations that are critical for graphics. Well, it just so happens that those same calculations are also critical for doing the kind of back propagation computations that you have to do in neural network computations. So people, and you probably heard it, you've ever heard of Bitcoin mining, that's the same thing, same kind of computation. So all of these things kind of just hop on the GPU and do things that aren't graphics because they're fast and they're relatively inexpensive compared to the same amount of compute power in a computer. So now that stage is set, basically a neural net is really a simple thing. It's you have an input layer and each of the circles in the red input layer, I'm going to call them X1, X2, and X3. It's just a number. It's a real number, real valued number. And you feed it into what's called a hidden layer. And the hidden layer, that's one of the parameters that you set. You have you can decide how many nodes are going to be in the hidden layer. It could be 1, it could be 1,000, whatever. And then the way that you compute is that the hidden layer itself has a function in it. And what it does is what the arrows represent are a contribution from each term from the input layer. And the way that contribution happens is a linear combination. So there's a weight on each input for each hidden layer node. So the node at the top, H1, is whatever this function is. We haven't decided what it is, but it's a function of the combination of the weight for the first input, the weight for the second input times the second input, the weight for the third input times the third input. So this equation at the bottom. And then you do a similar thing, you combine them. There's another function on the output layer, and that gives you your output. So it looks complicated. There's arrows going all over the place, but in reality, it's just a simple, like a weighted average type computation, very basic mathematics. And so the trick in the hidden layer is it's not really such a big deal, but you have to pick a function that goes in the hidden layer, and what it does is it adds some nonlinearity, and it allows the neural network output to fit more complex functions. And so a couple of things that are used, one is called sigmoid, and sigmoid is basically an approximation of an on-off switch. So for very small values of the input, it's 0, and then for very large values of the input, it's 1. and that's really all it amounts to. The reason that the sigmoid is used is that, well, we'll see in a moment when we start doing back propagation, you need a function that is differentiable, makes it easier. If it's differentiable everywhere. So that's sort of where the sigmoid comes from. And then there's another one, I can't remember what Grell used to use. I think it's for relational linear unit, something like that. But it's basically, it's zero for negative values, and then a linear equation to the right for any positive input value. And that's really what this is sort of maybe the magic, I guess, of a neural network over just like a linear function like you do in linear regression, is to have these functions, these hidden layer functions. And there's actually a theorem was proved in the late 80s, I think 89, which says that if you increase the number of hidden layers sufficiently with a one layer neural network, you can approximate any complex nonlinear function. So that gave people confidence, that hey, we can use these neural networks for all kinds of things. It doesn't just have to be linear models, which all of the historic stuff is associated with. So basically we have the network set up, the description of the network set up, and the question is, how do we find the weights? The weights really are the model. I mean, in addition to the hidden layer function, but the weights are the variables. So you're trying, when you take data, you give input and give output, and you try to say, what selection of weights gives me the least, like minimizes my error in predicting or classifying or whatever I'm trying to do in the network. And so the way to do this is, first you just pick any old random values for the weights. And it's actually important that they're random, because if you select 0, the algorithm actually won't work at all. It'll just spit 0 back out at you. So you just have some random number generator generate a value for all of the weights, and then you calculate the output, and then you compare it. You compare that calculated output to the output that you were supposed to get, and then you just simply adjust the weights to reduce the error. So the big question is, how do you do that adjustment? And the answer is sort of a complicated one, which is that you have to take the equation, those equations that I showed, which is a huge set of nonlinear equations, and you have to calculate for each weight the gradient with respect to that error, and you go in the negative direction so that you're minimizing. So it sounds complicated, just negative direction of the gradient, but the good news is that, like, outside of a class, you'll probably never write. You'll probably never have to calculate this derivative or write any code to calculate it, because they're all, that's all set up. That's like standard part of TensorFlow or Theano or Caffe or any of the libraries that that will fit models, that they do this back propagation on that. And so when you do step number 3, there's a parameter called the learning rate, which it's basically a fractional, it's like a small fractional number, 0.01 or something like that. And that adjusts, how far in that direction you go to reduce the error. And so what you pick the smaller, it turns out the smaller the learning rate, the better off you are. And you just repeat this for every data point you have. And not only that, you'll do what are called epochs, which just means take the data set and run through it again. You might take the same data set and run 1,000 times, go through all the data points that you have, trying to fit your model. And what you do is you watch You watch to see how your error rate changes. You watch to see how your random weights change. And when they settle out, that's typically when you know you're done. So that's just a neural network. But they didn't really work that great in Gaze. We have to go deeper, and really there's nothing to it. It's just adding hidden layers to the neural network. So instead of our hidden layer 1 outputting to the output layer, we add a second hidden layer, and you can repeat this. You can have 3, 4, however. Usually you see 3 or 4 hidden layers in a lot of deep learning projects. And that's it. It's the same It's the same set of algorithms for back propagation. It's just more of them. The complication really between going from this to this is that the amount of data that you need to fit the model grows exponentially. So if you needed 100 data points to fit the first neural network, you're probably going to need 1,000 or maybe 10,000 to accurately fit all of the weights in a deep neural network. So I'm going to move on to applications, and when you move on, when you
Can I ask you a question?
yeah, sure.
So you got all those little circles. Every one of those circles is just some function.
Yeah, that's right. So the red and the green,
Oh, blue circles.
they're numbers. But yeah, the blue circles are also numbers, but yeah, there's a function in there which is this.
Yeah, well, one of these functions. And
Yeah.
there's 10 or 20 or 100 of these things.
Right.
And the standard codes that are being used for data.
Exactly. Yeah.
And so, I guess you can select which block of functions you like to use. But they're all kind of pre-established at this point.
Yeah, it's usually either sigmoid. There's one called softmax, which is very similar to sigmoid. It's very commonly used. And this ReLU is very commonly used now. Sigmoid used to be used a lot before, and then inverse arctangent has the same sigmoidal shape, but it's basically like a bunch of different functions that approximate this, binary switch, and whichever ones are the ones that are favored usually tend to be like the ones that are the easiest to compute, the easiest to differentiate. So because you're doing these calculations like thousands and thousands and thousands of times over and over again. So if it's 10% faster to do sigmoid or softmax or whatever, that makes a difference.
So you run all your data through some random weighting of all functions. You get an output, you just say output minus my actual number is so much.
Exactly. And then depending on the size of that,
You're minimizing just the actual value of that by adjusting your weighting functions up and down.
Right.
Not like squared value. Some other relationship with that value.
well, you're not looking at, you don't really have a loss function like you would in regular optimization. All you're doing is you're saying, like, I know that if I move my weight in a certain direction, it's going to reduce the error. Right. So I know the derivative of the functions that I'm using. So I just say, or I can calculate it using some kind of difference approximation or whatever. I'm just saying, like, I know if I in this case, I know if I decrease W11, it's going to make my error less because I know what that gradient is. Or if my error is positive, obviously the sign of the error matters, but it's just the amount of the error just weights sort of how much you go in that direction, and then you also have this learning factor that you can use to tune as well. And so it's really just, it's kind of there's not really any fancy sort of like theory or mathematics behind it. Behind the idea of it, it's just like, here's this thing. Now you do the simplest thing, which is go in the direction that makes it better.
eventually gets there.
if you do it long enough. And I mean, there's problems, right? It's essentially, I mean, it's a huge nonlinear problem. So it's, if you think about it geometrically, it's non-convex, and you've got all these local minima everywhere. You can kind of get stuck, and you don't know, you know, you're not really at the best model, but you can't go anywhere because everywhere is uphill. And so there's tricks that they do, like this trick called dropout, where you just erase some of your model parameters halfway through the. I don't really understand all of them. I mean, I think the idea behind dropout is you're actually training other parts of the network to sort of compensate for whenever you drop these neurons out, much like I guess your brain would, you know, try to compensate if you have some injury or something. Or you can do, there's a thing called stochastic gradient, which is the same idea, but you add sort of a random perturbation, and that helps you get out of these local minimum spots and move on to something else. Thanks, that was a great question. So convolutional neural networks, they're basically, so like what I'm showing here would be sort of the equivalent of a three-layer neural network, three-layer deep network. And convolutional means, I don't know if this is the greatest graph, but if you can see all the way on the left, it says faces. First column is faces, then cars, then elephants, and then chairs. And if you look at the bottom, this is probably also hard, very difficult to see, but the bottom they're all the same. It's the same set of convolutional neural networks. And the idea here is that you set this convolutional structure up in the neural network so that you get what are essentially filters. Okay, so the word convolutional refers to this idea in image processing where you have like a mask. It's like, it could be like, say, a 5 pixel by 5 pixel mask, and you run the mask over each pixel of the image and multiply the values in the mask by the values of the pixels in the image, and the middle one in the middle you put the result of that computation. It's just it's kind of like a filter, like you could do a blur filter or some kind of sharpening filter or whatever. But when you do the filter, you convolute with these particular filters that are shown at the bottom. What happens is when you find parts of the image that have the same structure, it basically, the computation will go to the maximum. It's basically showing you got a match, right? This part of the image looks exactly like the filter. And so all of these guys at the bottom, they're essentially edge filters. So you've got like edges pointing in different directions. You've got like one that's just all white. You've got one that's like a black circle. And so it's that that part of the neural network is doing something very fundamental to the image. It's saying these are the parts of the image that are interesting to identify. And what's really interesting about it is this is typically something that when you do a deep neural network, the neural network itself identifies these for you, what these filters are. Whereas in the past, when I mentioned feature engineering earlier, engineers would actually build these things, build these filters. But now in deep learning, you set the structure up, and it will come up with these little filters for you. Okay, and so then when you go up one level, then you build another set of filters, and these filters are basically combinations of the filter below. So now you've got, if you look to the far left where the faces are, you've got structures that represent like an eye or a nose or lips. So individual parts of a face are composed of these smaller parts at the bottom, edges and circles and white space. And then when you get to the top, which is where your classifier lives, then you can see the more complex structures, which are the actual faces that are in the image that were fed to the neural network. And similar things are going on in each of the other, in each column of this. So cars have a different set of, even though they start with edges, white space, dark circles, when you go up to the next level, they've got different, subparts of the picture that help you identify a car. And at the top, you have, more complete masks that look like the actual cars themselves. I'm not going to belabor that, but the very interesting part of this is that is looking at the bottom and seeing, like, here I've got these edge filters that I'm using on different classification problems, right? So, and that has sort of led to this idea of transfer learning. And the idea behind transfer learning is that you can compute, someone can have maybe spent a long time doing these computations to compute all of these convolutional layers of their neural network, and you can just come to the end, baby, and pop that last classification layer off and train your own. Now, instead of training, all of these, remember I said it grows exponentially when you add another layer. Now you don't have to train all these other layers. You're just training one additional layer. It's faster, it's easier. You have some, depending on who built the layers below, you might have some additional confidence. If it's Google's model that you just pop the last layer off of, it's probably a pretty good model to start from. So that's one class of deep learning, and that's been very, very successful in image classification and that sort of thing. I don't really know too much about recurrent neural networks.
So there's standard packages out there for image analysis that Google somebody
Yeah,
sell
absolutely.
you for a few bucks.
No, it's free. And they have a GitHub repository, and it's got all their, like a bunch of training. TensorFlow, that's right. It's got all of their trained models, or not all of their training. It's got a lot of trained models in it. Like they have a model, I'm going to use at the end, the model they have trained on this large scale visual recognition problem, and we're gonna take that model and just pull some images off the internet and feed it to the model, see what happens. But you can also take that model. There's actually an exercise. There's a tutorial exercise on the website that probably one of the things we'll do on June 3rd if we go down this road with deep learning, and it shows you how to take that last classification layer off and train it on an entirely new set of images. So, recurrent neural network, the idea there is that the output of a layer feeds back around as an input. So you can see there's the hidden layer at the top has Y1, Y2, YT, and then at the bottom there's U1, U2. And these U nodes just serve as additional input. And what this graph is trying to show is that there's really like an expansion. So you might have one node for the first word in a sentence, and then another node for the second. And what's happening here is that the middle layer is predicting a word, and then the next layer, the word that comes after is going to depend on the word that came before, right? So like, sometimes you can predict the next word somebody's going to say, or you can say it's definitely not going to be this one, whatever, and that's what's going on. It's used in current neural networks are used in heavily in natural language processing.
I can say that the Coursera Data Scientist Toolbox Capstone Course 9 class project, you do something that predicts, like on your phone, right? You start typing things in, it starts giving
Right.
you words to start, that it might be next. And so that was one of the projects in that course. So it's
Cool.
pretty cool.
You did a recurrent neural network or something like that.
Something like it. So yeah, and then you make a Shiny app, so you put it up on the web, and then you can play with it, and it was like a website, you know. So you
Yeah.
type in my house is
Okay.
on
Okay.
fire, you know, whatever. So and you got graded on.
Yeah.
They ran a set through it, and you had to hit a certain match rate and stuff. So it was pretty cool. I have it. I can show that one time too.
So, I mean, it seems great, like, they work for everything, they're awesome, they do things that previously were thought impossible, so what are, obviously this is not, there's no free lunch here, and really the biggest thing about deep neural networks is that it takes tons of data. I mean, you can't just, it's not like a linear regression problem where you can take 100 data points and you're done. And really the problem with that is if you have what's called a supervised learning problem. A supervised learning problem means like we give the algorithm or the model the data, the input data, but we also have to tell it what the output data is. So that's called labeled data. The outputs have labels on them, either like classified, they're either classified or they have some values, like if you're trying to predict somebody's income maybe. And that's like, to do that with a lot of data, like imagine having to go through 150,000 images to say that they're, whatever, this is a panda, that's a zebra, this is a tiger. That's very expensive to do. And that's probably the data issue is probably the hardest part of deep learning right now. Another problem, which kind of makes me uncomfortable, I think it makes a lot of people uncomfortable with these models, is that they're more or less black boxes, right? There's no physical explanation for what's going on inside of the neural network. So it's really hard to explain, how it's working, why is it working, what could cause it to fail, and then the last thing is performance, because these models end up being really big. There's a lot of operations to get a prediction out of them, and just to even process the input. You can't just run like a general deep neural network model anywhere. So like, probably remember early on when Siri and Google, OK Google on those phones, and I think you still even have to be in some cases, maybe all the time. You have to be connected to the network. Like the phone's not going to just, you can't have a program on the phone that's going to recognize your speech. So you gotta have a network connection, and it's gotta go back, figure out what you said. And I think they do some caching now on the phone to make it work better. But in general, like mobile devices are very limited. It's easier on computers, but even in some cases, if they're big enough, that would be.
So on those, do they take the speech and convert it into a hash and send it? Or are they sending the full?
I don't know how to send that. So going back to the issue of like how and why they work, this is something I wanted to point out. I recently came across a paper, and this paper is called "Why Should I Trust You? Explaining the Predictions of Any Classifier," and it's about a deep learning image classifier, and this classifier misclassified a husky as a wolf. Okay, so that's the image on the left, husky classified as a wolf. And so when they went back to figure out what parts of the image were critical in making the determination that it was a wolf rather than a husky, they ended up with the pixels shown on the right-hand side that say explanation. So can anybody think of a reason why those pixels might be significant? It's really, really kind of interesting.
Snow?
Exactly. Exactly. So when they went back to their database, they discovered that almost all the pictures they had of wolves had snow in them. And almost all the pictures they had of huskies, were in somebody's backyard or, in a house and so the classifier ended up training itself on images of snow as, identifying wolves. So to fix this problem, we had to go back to their data set and add more pictures of huskies
In the snow.
in the snow and more
Much.
pictures of wolves not in the snow, to de-emphasize that issue. And actually something really interesting, this is kind of like newer stuff that I've heard about, but I don't know that much about it, is that there are programs called generative adversarial networks. And what they do is they generate, that's the generative part, they generate adversarial images for classifiers. They're neural networks that generate adversarial images. So they would generate something like this, and to try to trick the classifier into thinking that it was a wolf when it really was just a picture of snow or whatever. And
Okay.
and they take those images and they add it to the data set. Like it's okay to, I mean, they do all kinds, usually with images to get around the data issue, you do things like you flip, you'll flip it. You'll, do all these symmetry things to try to get around this problem that A, you have to label the data, and B, you need a lot of it. So that's, kind of general, these GANs, they're called, are trying to address this problem where you train a network and you don't know like exactly what is making it say this thing is like what are the features, what are the sort of hidden features of my data set that I don't know about that are tricking this classifier into thinking it's something that is really not. So, but obviously, these things are really cool, and they're basically getting around stuff that took a huge amount of effort, like featuring media. You would spend months and months coming up with different ways to identify different parts of images or different parts of I don't know what you call the people speak and you have a recorded audiogram or something like that. But yeah, so like you don't have, it's figuring some of that stuff out for you. You're attacking these complex nonlinear problems that you can't. It's more difficult to handle with traditional data science techniques. And interestingly, in a lot of cases, even though we use humans to usually label the data, but in the end, the model can outperform humans. Like there was a recent paper about dermatologists. They had a set of scans and they knew the outcome, whether the person had skin cancer or not, and the model outperformed expert doctors in reading the radiographs. So what do you use to do deep learning? You can do it pretty much on any platform. I think a lot of people use Linux because it's kind of academia mostly is where this stuff comes from, and there's a lot of freely available stuff. But as far as languages, there are lots of other languages that you can use. I happen to know the Python tools and libraries because that's been in every class I've ever taken about machine learning. And so the big names are there. So as far as like setting up the graphs and doing the backpropagation, you have TensorFlow, Nano, PyTorch, and Caffe. And that's basically for saying like, what does my network look like underneath? And sort of doing, it's not really plumbing level stuff. It's not like matrix math or anything like that. it's higher than that level, but Keras is a higher level language. It's kind of, if you know, you ever heard of Hadoop and Pig, it's kind of analogous to that. Hadoop is like the level data processing. Pig is a language on top of it, or I don't know. Anyway, I thought I would show real quick. On the TensorFlow website, TensorFlow.org tutorials, they have this image recognition tutorial. And I'm not going to go through the whole thing, but it's basically this large visual recognition challenge where they had 1,000 different classes, zebra, Dalmatian, dishwasher, etc., and did this identification. They have a model that's available. You can download it. I'm trying to find. Anyway, if you just go to this, go to TensorFlow.org and look for the tutorials, you'll see this image recognition. Got a link on here to the model, which I've already downloaded the repo. And, you can see it says it's got to download this model, which takes about 200 megs of space. So I've already done that, so we didn't have to wait for it to download or anything. And then you just use this Python command, and you pass in an image. So you can use this option image file to pass your own image to it. And the other critical piece of information is that I don't see it in here anymore. I just happen to know this maybe. I don't know. Maybe it's at the bottom. It expects the images to be 299 by 299. Oh, here it is. Yeah. So the model expects to be square 299 by 299 images. So one thing you can do is if you want to search for zebra images on Google, you can go to tools. Just go to images. So now you're looking at images of zebras. You can go to tools and you can set the size. So you can set the size to be exactly 299 by 299. And it gives you some images. The other thing too that I found out using this model is that it has to be a JPEG file. Like PNG.
Type drop down to probably starts with.
Yeah, it's a different. It's like things. So anyway, I downloaded a few images. I downloaded this one because I thought that's kind of challenging. It's a kid in a zebra costume. I downloaded this one, which is sorry, you probably can't see this. Downloaded this cartoon image over here to the right. Sorry, that's one. This is one, and this chair. This I wanted to see, this is, and they're on my desktop. So I have them here, just on my desktop, already downloaded them. And so you just run this Python classify image.py, which is in the repository to download, and pass it the path to the image file, and just let it run. And so what it spits out, besides some warning messages, because TensorFlow is built for like the least common denominator chipset, so it's telling you you have a better architecture, it'll run faster if you recompile it. So I can recompile it, but at the bottom it spits out this the top 5 guesses that it has. So you can see this was that was for the chair, and it says that's a studio couch or day bed. So pretty good. It's not a zebra. See what else.
Interesting. The next closest score is way less.
Yeah,
that's a wardrobe.
So there's 1,000 classes. So that 1,000 classes and all the predictions will sum to 1. So 72% likely to be the couch, and then the rest of the 28% is spread over
Just wild. Yes.
999. So, yeah.
Does it say how many images, original images, went into the live?
Yeah, it was 150,000 for 1,000 classes, so that's about 150 per category. So the kid, Zebra Kid, same errors. So this time it says Zebra, and it's, I mean, there's not much of the kid showing, so, but you can see that it's a lot lower score.
It's not real high confidence.
And usually, like a lot of times, you'll have like a 50% threshold if you have a small number of classifiers, and you might say, like, you might want to return undetermined for this image. I don't know.
That would be one to see what part of the image it thought was most important.
Yeah, absolutely. And then the last one, which looks like it's a cartoon zebra, but
It's a zebra.
I want a zebra, right? And so comic book is your
Yeah. And
is your top score. So obviously there are features that this comic aspect, probably like the nose is too rounded and fat around.
even that, it wasn't highly confident on. I don't really know what this is.
So anyway, I think it's kind of neat. I mean, it's like you don't really have to do any work. You just have to. Well, I say that you need to install Python at least, and you have to install TensorFlow, which that's if you install Python, it has a thing called pip, which is like it's just a tool for downloading and installing. So you can install Python, install pip, and then do a pip install TensorFlow. You'll have what you need. Download this repository from the tutorial, and you can find your own images and send them to this script to see what it says.
You running this right off Mac OS?
Yep.
See, I had a problem with I had to install everything there because I couldn't get it to install TensorFlow well on the. I tried a couple of trade Debian, and now I'm blanking on the one I ended up getting to work. But I had to do it all native.
Yeah.
But it all went in fine on that.
Yeah, this is just. I think I'm on your side. Maybe scale.
Because I got the same errors, but it ran.
Yeah, well, scale.
I would say Mac is going to be more difficult, typically, than a general Linux distribution.
Yeah.
I would think it should all work easier. I would expect to have more problems with a Mac and having to go homebrew or some crazy thing to get things installed.
Yeah.
There's been a lot of trouble with everything.
On this, it just seemed to, I'm trying to remember now what the library was. One of the libraries that TensorFlow kept wanting that it even got flaked out on.
What, was it a current, a late version of the OS or?
Yeah, it was the required one.
Well, and then you end up with an OS version that's ahead of a Python version. So, or some you
and
could.
that was another one. Which version of Python did you run? 3.3 or 2.5?
So I run Anaconda, so I have a bunch of 3.5 for this particular one.
Because I did 2.7 because it said that was the one it was looking for.
Anyway, so that went a little bit longer than I had anticipated, but if you guys have there's any more questions or discussion, you can certainly entertain it. And we had planned in 3 weeks to maybe go through something on June 3rd, which there's another exercise, another tutorial, which is, like I said, it's a transfer learning where you strip the last layer off the network and you provide it with another set of images, and then it classifies those images. And I think it said in about 30 minutes or so to do that, to fit the model. But to do that, you need to have Python installed, you need to have TensorFlow installed, and you need to download the repositories. You need to either know how to use Git or I think there might be a downloadable file. We can go through all that stuff during that, or if, we'll be here in one way or the other. We can work on a project or whatever.
That might be a good way. I mean, great show of hands. Who knows Git?
Git?
Yeah, sort of. Right. So that might be useful to, hey, here's what it is. Here's how you sign up. Here's how you get a repo checked out.
Yeah.
I mean, just some of the basics to get it together, and then it just build on that time after time kind of thing, and get everyone to a level where they're just ready to go. You show up and you just can start working on a project. I was going to say project-wise, with all of this classification. There's that Kaggle project. No, or maybe it's good. But if it's not, then it's NOAA, marine fisheries, trying to identify 3 kind of fish in an image. And it's $100,000 if you win it, kind of deal. There's a reason, if that's still running. I think it probably is, but it's very similar to all of this, which would be actually something. It would be something to go try and do. So building the environment, installing Python, which there's bumps in the road of installing Python and TensorFlow and getting it just to play nice with this, and maybe do that tutorial. That kind of gets everyone.
What does everybody have? You have a PC, right?
Yeah.
Okay. And what about you? Windows?
What do you want? Well, there it is.
All right, so maybe I can learn Windows.
I know some Windows.
Sorry, I've been an iOS developer since 2009, so I haven't seen a Windows machine since maybe 2011 or something.
Not missing much.
Here's the question. We got to send you over to Spencer and into SM Mug. How many have your Windows machine dual boot to Linux?
I did. But I had.
Now you're talking. Now you go straight into Linux and you got something working.
Yeah, I mean, I think Windows is fine.
Yeah, that'll work.
I think you don't have to install Cygwin to do it anymore, right? There's tools for that, aren't there?
Download Git shell.
In shell. But does it set up something under the hood?
Yeah, it does.
It's using something under the hood to do what?
It's
Yeah.
like Microsoft has some type of command line bash program.
Oh,
You know,
okay.
like PowerShell or something.
Okay.
Yeah. I think I had to do it for Subversion or something.
Okay.
Anyhow.
Okay, so on June 3rd, we'll install FreeBSD on all of your laptops.
Oh, so you're going to send us back to the root of Mac OS.
That's right. That's all I'm going to say. No, I mean, would y'all want to do that? Or, I mean, we could, I think just getting your machine with Git on it, if you don't, you probably have it already. To where you can just like downloading some repositories and stuff. That's a pretty useful thing. I mean, you do that all the time professionally. So, and Git is very much the most popular source control. Okay, so let's do that, and then we can. If you guys, if there's a project like that, like a specific project that you want to work on, like if you have an idea or something, I mean, that's what's that?
I'll let you guys know.
Okay. It's always a challenge to come up with the next things. So, but we'll be here June 3rd.
Well, if you don't have one, I've got one. I feed you the